Hello and welcome to this revision session for AQA A-Level Physics on the topic of periodic motion, which is found in paper 1 of the course. So in today's revision session we're going to be looking to answer examination questions on A-Level Physics paper 1, in particular those questions on periodic motion. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions for periodic motion, assess your understanding on A-Level Physics for periodic motion, and understand what topics of AQA A-Level Physics in the concept of periodic motion you need to improve upon. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. Okay, and then in this section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure to write these answers in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should we revise for your A-Level Physics? The first step is to learn the key facts. Use the revision guides, the class workbooks, the student prep notes and the textbooks to learn the key ideas of the course, and you might wish to write mind maps and write out notes for yourself. Now the second step is to test yourself, so that's to use things like Caboodle, Seneca, student knowledge checkers, and quickly test your knowledge. You might even want to make your own cue cards to do this. Then the third step finally is to practice exam questions, so use things like exam prep books, homework books, supervised study books, additional workbooks to help answer examination questions and mark your own work. You may even wish to download your own examination past papers to do this. Okay, so the three steps of learn the key facts, then testing yourself, and then practicing exam style questions are how you should be revising A-Level Physics. Now in this revision session we're going to have a look at three different types of questions. The first types of questions are the general check questions. These are the basic questions designed to probe your understanding of the key concepts of the topic. Then we've got our checkpoint question. These are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts. Then finally we've got assessment point questions. These are past paper examination questions which will mimic the types of questions found in public examinations. So let's now start to look at the concept of periodic motion. So state and justify whether the following oscillations show simple harmonic motion. So you've got a basketball being bounced repeatedly on the ground, a guitar string vibrating, a conducting sphere vibrating between two parallel oppositely charged metal plates, and the pendulum of a grandfather clock. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, remember what the definition of simple harmonic motion is, and that's the idea that there's a restoring force which acts always towards the center of the equilibrium or the oscillation, and the size of this restoring force is directly proportional to the displacement is from the center equilibrium position. So the first one is not simple harmonic motion because you've got constant acceleration of the gravity towards the ground, but not when it's hitting the ground or when it's hit by the player, so it's not going to follow those rules. The second one, a guitar string vibrating, yes that is, there's always a restoring force towards the equilibrium point and it is proportional to the displacement from that point. The third one isn't simple harmonic motion because it travels with a constant acceleration towards each plate and then suddenly reverses its direction of velocity upon hitting the plates. But the last one is simple harmonic motion because there's a restoring force directed towards the equilibrium point and it is proportional to the displacement from that point. The next question says, in each of the examples below, give the phase difference between the two curves shown and then indicate that as a fraction of an oscillation, then have it in degrees and then give it in radians. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can see that the two oscillations have a difference of half a cycle. Now we know an entire cycle is 360 degrees, so it's 180 degrees, and an entire cycle is 2 pi radians, so this one is pi radians. You'll see in the second one, each of them is out by a quarter of a cycle because you can see that one of the waves is a quarter of a cycle ahead compared to the other wave at that particular point. So they've got a difference of 90 degrees and they've then got a difference of pi over 2 radians. In the last one, it's a bit more challenging. You'll see that actually the cycles are different by 3/8 of the cycle. So when you do 3/8 times by 360, that's 135 degrees, and do 3/8 times by 2 pi radians, it's 3 pi over 4 radians. The next question says the figure below shows two oscillations which are out of phase. By what fraction of an oscillation are they out of phase? And why would it not make sense to ask the same question about the third figure in this particular diagram? So pause the video now, then unpause the video when you want to go through your answer. Right, so okay, you can tell that they're out by half an oscillation in that B figure, because you can see that that one of the oscillations is a half of a wave cycle ahead of the other one. Now, you can't ask the same thing about the one at the bottom, figure C, because you'll notice that the two waves have different frequencies, so they're not going to be coherent because their phase difference is continually changing, so you can't compare their phase difference. The next question says the pendulum of a clock is displaced by 4 centimeters and it oscillates in simple harmonic motion with a period of 1 second. Firstly, write down an equation to describe the displacement of the pendulum bob with time, then calculate the maximum velocity of the pendulum bob and then its velocity when its displacement is 2 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, this first one, it is an equation which we do cover. So it's actually going to be x is equal, the displacement is equal to the amplitude times by sine of 2 pi t for this value, and then we know that actually the amplitude in this case is 4 centimeters, or 4 times 10 to the minus 2 if you want to work in meters, and then you can work out your answer that way. Now the maximum velocity, we again are given this equation on our equation sheet. It is 2 pi f times by the amplitude a, so we do 2 pi times by 4. We know that the frequency is in fact 1, because there is one oscillation every second, so therefore it's 25.1 centimeters per second. And then its velocity, well again we know we can work out the velocity with the equation for the actual value, which is going to be equal to 2 pi times by the square root of the amplitude squared minus the displacement squared. So you pop in all those values and you get 21.8 centimeters per second. The next question says use the graph shown in this particular diagram to determine the values of the following quantities: amplitude, period, maximum velocity and maximum acceleration. So you can find the amplitude by the following. So in the first graph you can see its displacement against time, so that maximum displacement is going to be the amplitude, so it's 0.02 meters. You can find the period because the period is the time it takes for one whole wave cycle. You can find it out from any of the three of them, but you can see that it's 0.40 seconds. If we look at the displacement time graph, it starts at, you look at the peak at 0.1, goes to the next peak at 0.5, so therefore must be 0.40 seconds. You can find the maximum velocity by looking at the max point on the velocity time graph for an oscillator. So you can see it's 0.31 meters per second, and then you can find the maximum acceleration by once again looking at the maximum point on the acceleration time graph, so it's 5 meters per second squared. The next question says state what point in an oscillation the oscillator has a zero velocity but a positive acceleration, and then look at the displacement time graph below. When the time is 0.1 seconds, what is the gradient of the graph, and state the velocity at this instance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when does it have a zero velocity but a positive acceleration? Well, it has a zero velocity at a maximum displacement. So the extreme left, the maximum negative displacement. Now it has to be the maximum negative displacement because the acceleration has to be acting towards the center, so therefore it must be a positive and going towards the right. I mean, you could also have it vice versa if you've altered your positives and negatives, but they've got to be in opposite directions. Now in this one, you'll see at 0.1 seconds, the gradient, you can work it through, is going to be 0 because it's at a maximum point. So therefore the velocity, which is the gradient of a displacement time graph, that's revision from the mechanics module, is the same value. The next question says, the figure shows the displacement time graph for an oscillating mass. Use the graph to determine the following quantities: the velocity in centimeters per second when time equals 0 seconds, the maximum velocity in centimeters per second, and the acceleration in centimeters per second squared when the time equals 1.0 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see at time equals t equals 0 that the gradient is in fact going to be equal to 0, and the gradient is the velocity of the particular object, so therefore our answer is 0. Now, what's the maximum velocity going to be? You can tell it's actually going to be when you're going through 1 second there, because that's going to be when it's at its highest gradient. So what you can then do, so it therefore is work out the gradient at that point, so it's 47 centimeters per second. And then finally, when t equals 1 second, you can remember the premise of simple harmonic motion is that displacement is directly proportional to the acceleration. So you'll notice here that actually at this point here that we're going to have at the value of t equals time equals 1 second, because the displacement is 0 and the acceleration is directly proportional to the displacement, well, the acceleration will also be 0 as well. The next question says, determine the frequency and the period of the oscillation described by the graph in the figure below. Use a copy of the graph and on the same axis sketch the velocity of the particle and the acceleration of the particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to remember, how can you work out the frequency and time period? Well, the time period is going to be the time it takes to go from one point on the wave to the next point on the wave, which is the same. So therefore, in this case, the time period is 8 milliseconds. Frequency is 1 over time. You convert your milliseconds to seconds. 1 over 8 times 10 to the minus 3 is 125 hertz. Now, from the graph, how can you work it through? Well, you've got to remember firstly that in your acceleration graph, you've got to remember the acceleration is directly proportional to the displacement in the opposite direction. So you can see here the blue line represents the acceleration, and it's in the opposite direction to the displacement at all points. Now, the velocity, you'll think about it, is staggered across. So you'll think, remember, there's a phase difference here, because when the displacement is a maximum, the velocity is a minimum, and when the displacement is 0, the acceleration is a maximum. You can plot those points and sketch it through, and you get the red line as shown. The next question says, the figure below shows the displacement of a body as it vibrates between 2 points. State and explain where the body is moving with simple harmonic motion, and then on a second set of axes on your copy, show the velocity of the body as it vibrates. Then on the third set of axes on your copy, show the acceleration of the body. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's not going to be simple harmonic motion, because simple harmonic motion shows a displacement with a sine or cosine relationship with time. So you'll notice in this displacement time graph, because it's not that sine or cosine value, you don't have a directly proportional relationship between the actual displacement from equilibrium and the actual acceleration of the object either. Now you'll notice that in the velocity time graph, well, the velocity is going to be the gradient of the displacement. So you can see here that at some points you've got a constant gradient in your displacement time graph. So you have a constant velocity. Then you'll have a 0 when you'll have no gradient of the displacement time graph. You've got a 0 velocity, so it works through as such. Now the acceleration time graph is therefore again going to be linked to the gradient of the velocity time graph. So you'll see at the start here, you've got no gradient at the velocity time graph, so you've got a 0 acceleration. You then got a very steep gradient on your velocity time graph, so you'll get that acceleration. Now you'll note that the acceleration is in the opposite direction to the displacement, as shown in the displacement time graph. So when the displacement is a positive, the acceleration produced will be a negative, and it works through as shown. The next question says, an object moving with simple harmonic motion goes through 2 complete cycles in 1 second. Firstly, calculate the time period, then the frequency, and then the angular frequency. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know that the time period is the time it takes to go through one complete cycle. So therefore, if there's 2 complete cycles in 1 second, well then the time period is going to be 0.5 seconds. Frequency is 1 over time period, so it's 1 over 0.5, which is 2 hertz. Then the angular frequency, much like circular motion, is 2 pi f. So therefore it's 2 pi times by 2, 4 pi radians per second. The next question says, the figure below shows the displacement time graph for an oscillating mass. Use the graph to determine the following: the amplitude, the period, the frequency, the angular frequency, the displacement at A, the velocity at B, and the velocity at C. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, you'll see the amplitude is the maximum displacement, 0.20 meters. The period is the time it takes for the wave to repeat itself, 0.4 seconds. The frequency is 1 over the time period, 2.5 hertz, or 2.5 seconds to the minus 1. Angular frequency is 2 pi f, so therefore it's going to be 2 pi times by 2.5, so 5 pi radians. The displacement at A, you can then work it through off the graph by measuring it. It's minus 0.1, minus being important because it's displacement, so it must have a direction. The velocity at B is going to be the gradient of your displacement time graph, so therefore it's 0 meters per second. And then the velocity again is the gradient at that point, so it's 3.1 meters per second. The next question says, to start a pendulum swinging, you pull it slightly to one side. What kind of energy does this transfer to the mass? And then describe the energy changes that occur when the mass is released. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know it's been pulled to the side, so it's been pulled away from equilibrium, so it's gained gravitational potential energy. Now, when the mass is released, we know for a simple harmonic oscillator, the gravitational potential is then transferred to the kinetic energy. That then reaches a maximum when the ball passes through the equilibrium, the lowest point, because that is maximum velocity. Then this kinetic energy is once again converted back to gravitational potential in a cycle. The next question says, the figure below shows how the different forms of the energy change with displacement during simple harmonic motion. Copy the graph and then show how the graph would differ if the oscillating masses were only given half the initial input of the energy. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be aware it's going to follow the same pattern, but now the total energy is half that, so the horizontal line goes to half the value, but the potential and kinetic still follow the same pattern. But it's important to note that for both instances, the maximum displacement of the oscillator is going to be less, but the relationship is not directly proportional, so it doesn't go to half. The next question says, sketch a graph showing how the kinetic energy and the potential energy of a mass spring system varies with displacement. State any assumptions that you make. Label the amplitude and maximum minimum kinetic and potential energies. Then the total energy of a mechanical oscillator is 1.6 joules. State the maximum values of its kinetic energy and potential energy. The oscillator has a mass of 0.120 kilograms. Calculate its speed when the potential energy of the oscillator is 1 joule. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's the same graph that we had before. So you'll see on here, the total energy remains constant throughout, and the kinetic and potential energies will overall add to the total, but they'll go from maximum to minimum in inverse patterns. So when the kinetic is a maximum, the potential is a minimum, and vice versa. Now the next one, what's the maximum value of kinetic energy and potential energy? Your maximum kinetic energy comes when the potential is 0, so therefore it's 1.6 joules. And whilst the maximum potential energy is when the kinetic energy is 0 joules, so therefore that is also 1.6 joules. Now this next one, you'll see here that we know that the kinetic energy is a half mv squared, but what's the total kinetic energy going to be? Well, the total kinetic energy going to be is the total energy overall minus the potential energy. So it's 1.6 minus 1, so therefore it's 0.6 joules. So we say 0.6 joules is the kinetic energy. So therefore V equals, it's the square root of 2 ek over m. We've rearranged ek as a half mv squared. So we get 3.2 meters per second. The next question says, a short pendulum oscillates with simple harmonic motion such that its acceleration is related to its displacement by the equation A equals minus 300x. Determine the frequency of the oscillations. Then the pendulum of a grandfather clock swings from one side to the other in 1 second. The amplitude of the oscillation is 12 centimeters. Work out the period of its motion, the frequency, the angular velocity. Then write an equation in the form of A equals minus omega squared x to show how the acceleration of the pendulum weight depends on its displacement. Then calculate the maximum speed of the pendulum bob, and then calculate the speed of the bob when the displacement is 6 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we know for simple harmonic motion A equals minus omega squared x. So we can say minus 300 is equal to minus omega squared x. The x's will cancel through, so we now can say omega, okay, which we can work through here, is 2 pi f. So therefore, when we cancel everything through, we can then say, well, omega is going to be equal, okay, to the square root of this 300 divided by 4 pi squared, so we get to 2.8 hertz. In the next question, we've got to remember that the period is the time it takes for the oscillator to go from one side to the other and back to the original side again. So because it's going to one side, okay, in 1 second, it's got to go back, okay, to double it, so therefore it's 2 seconds. The frequency, therefore, is going to be equal to 1 over time period, 1 over 2, which is 0.5 hertz. The angular velocity is 2 pi f, so therefore it's going to be 3.14 radians per second. Next, we know A equals minus omega squared x, and we know omega is going to be equal to 3.14, so therefore it's going to be minus 3.14 squared times by x, so it's minus 9.87x. The maximum speed, well, we know from the equation sheet that Vmax is equal to, okay, the idea of omega, 2 pi f, times by the amplitude, which is x0 in this particular notation. So therefore it's 3.14 radians per second times by the maximum, which is 12 centimeters. So we work it in centimeters here, so therefore the speed is 38 centimeters per second. Then the speed, we know the equation is going to be equal to V equals omega times by the square root of amplitude squared minus x squared, pop in all the values, and we get 33 centimeters per second. The next question says, give one example of a free and a forced oscillation, describe how dampening affects the amplitude of an oscillating object, then sketch the graph of a displacement against time for a simple pendulum with firstly no dampen and then secondly with a small amount of dampen. So pause the video now, then unpause the video when you want to go through your answer. Right, so a forced oscillator is when you've got something driving the oscillation. So it could be a mass spring system attached to a vibration generator, Barton's pendulums, a person on a swing, whilst the free oscillation is something that just oscillates without a driving factor. So it could be a mass spring system, a pendulum, a ruler oscillating over a desk. Now dampening is important because dampening will reduce the amplitude over time because energy is dissipated out of the system and amplitude is an expression of the energy in the system. Now if there was no dampen, we'd see a sinusoidal pattern, so a sine curve with a constant time period and a constant amplitude. Now if you've got a small amount of dampening or light dampening, whilst the amplitude will decrease exponentially for your sine graph, the actual time period remains constant throughout. The next question says, when a cricket ball hits a cricket bat at high speed, it can cause a standing wave to form on the bat. In one such example, the handle of the bat moved with a frequency of 60 Hz and an amplitude of 2.8 mm. The vibrational movement of the bat handle can be modelled as simple harmonic motion. State the conditions for simple harmonic motion. Calculate the maximum acceleration of the bat handle. Given that part of the bat handle held by the cricketer has a mass of 0.48 kilograms, calculate the maximum force produced on his hands. Then the oscillations are damped and die away after about 5 complete cycles. Sketch a displacement time graph to show the oscillations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the definition? You've got to learn these. It's the idea that there is always an acceleration towards an equilibrium position in simple harmonic motion, and that the magnitude of the acceleration is proportional to the displacement from the equilibrium position. Now we know in simple harmonic motion, acceleration is equal to omega squared A, or in this case omega squared r. Now again, you've got to remember that the amplitude has to turn into 2.8 millimeters into meters, and omega is 2 pi f, so it's 2 pi times by 60. So when you work it through, you get 400 meters per second squared. Now we know F is equal to ma because in periodic motion, it still follows Newton's laws. So therefore F equals ma. You've just worked out A in the previous question. You know M from the information given. So it's going to therefore be 400 times by 0.48, which is 190 newtons. Now in this next one again, like we said, the time period remains constant throughout the oscillations, but the amplitude decreases exponentially, so should follow the following pattern. Next question. Sketch the graph to show how each of the following quantities changes during the course of a single complete oscillation of an undamped pendulum. Kinetic energy, potential energy, total energy. Then state how your graphs will be different for a lightly damped pendulum. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to think about what's actually going on. So the total energy remains unchanged throughout the actual oscillation. But when the potential energy increases, the kinetic energy decreases and vice versa, and they vary on that complete cycle as shown there. But that's an undamped pendulum. Now, if it was a lightly damped pendulum, the total energy of the pendulum would decrease over time. So therefore, the maximum values of kinetic energy and potential, because they're going from one to the other, but also being lost at the same time, would also decrease. The next question says, list 3 examples of situations where resonance is a problem and 3 other ones where resonance is useful. In each case, state what the oscillating system is and what forces it to resonate. So pause the video now, then unpause the video when you want to go through your answer. Right, so problems could be buildings and earthquakes. So the mechanical structure is forced to oscillate from energy from the waves of the earthquake, which could cause them to collapse. You've got components in engines, so at certain rates of rotation, parts of the engine may resonate mechanically, with this resonance being driven by the energy output of the engine. So this can lead to the components in the engine cracking or disintegrating, and then the engine can fail. The next one is positive feedback in amp systems. So if a microphone is held too close to a loudspeaker, which is emitting waves of the same frequency that the microphone is tuned into, i.e. the actual sound wave that's being put out of the speaker, well then the sound waves from the loudspeaker will force the amplifier to resonate and produce that positive feedback. 3 useful parts of resonance would be a tuned radio. So the electrical signal in a circuit is forced to oscillate by the incoming radio waves and resonate, and that allows you to hear the radio signal. You've got a microwave cooker where the water molecules are forced to resonate by the microwave with heat of the food. And you've also got magnetic resonance in atoms where the nuclei and atoms behave as magnets. They can be made to resonate by electromagnetic waves. Now each nucleus resonates at a different frequency because they've got a different number of components in their atoms, so therefore we can work out the structure of the molecules in MRIs. Next question says, sketch a graph of amplitude against the driver frequency for an experiment on a mass spring forced oscillation. Use the graph to explain the effect of resonance on an object. Explain why a glass shatters when exposed to a sound at the natural frequency of the glass. Then the side panel of a tumble dryer vibrates loudly when the dryer spins at a specific angular frequency. Explain why it only happens at a certain frequency and suggest a technique to reduce the vibration. So pause the video now, then unpause the video when you want to go through your answer. Right, so you should be able to remember the graph of the amplitude against the drive and frequency. The amplitude will increase as the drive and frequency goes to hit the natural frequency. The amplitudes of the oscillation are maximum when the natural frequency equals the driving frequency, that is resonance, and then once the driving frequency goes above the natural frequency of the system, the amplitude will decrease. So glass will shatter because glass will resonate, at the frequency when the driving frequency of the sound is equal to the natural frequency of the glass. That will increase the amplitude of oscillations because resonance is occurring. That amplitude becomes so large that the glass will break from it because it doesn't have the mechanical structure and support to hold it together. Now the next question, when you've got a spinning drum in a tumble dryer, that creates a driving force on the panel. Now the driving force on the panel is related to the angular frequency of the drum spinning in the dryer. So when the driver frequency is equal to the natural frequency of the panel will then resonate, so that to reduce the amplitude of the panel you can install dampener, because dampener will dissipate energy out of the system, so you can install rubber or foam pads to it. The next question shows the piston of a small car engine which oscillates in the cylinder with a motion which approximates simple harmonic motion at 4,200 revs per minute. Okay, the mass of the piston is 0.24 kilograms. Explain what's meant by simple harmonic motion. Calculate the frequency of the oscillation. The amplitude of the oscillation is 12.5 centimeters. So calculate the maximum speed at which the piston moves, the maximum acceleration of the piston, and the force required on the piston to produce maximum acceleration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's simple harmonic motion? Once again, it's that there's always acceleration towards an equilibrium position, and the magnitude of this acceleration is proportional to the displacement from this equilibrium position. The frequency, well, we know that there are 4,200 revolutions per minute. The frequency is the revolutions per second. It's 4,200 divided by 60, which is 70 hertz. Now we know that maximum speed is equal to r omega, so therefore we can do the value for omega, which is 2 pi f, so it's going to be 2 pi times by 70, times by r, which we can tell is going to be 12.5 centimeters, so therefore it's 12.5 times 10 to the minus 2 meters, so we multiply the two together to get 55 meters per second. We know acceleration from the equations is equal to a equals minus omega squared a, or minus omega squared r, because the amplitude is the radius in this example. So we can pop it through and get that to be 24,000 meters per second squared. We know that from if obeys Newton's law, so F equals ma. So you've got your value of A is 24,000. You know the mass in the question is 0.24. Multiply them together, we get 5,800 newtons. The next question says, doctors can use ultrasound to monitor the heartbeat of a baby when it's developing inside the mother. A baby's heart was beating at 142 beats per minute. The wall of the baby's heart was moving at a maximum velocity of 22 millimeters per second. Calculate the maximum displacement in millimeters of the wall of the baby's heart. Assume that the motion of the wall of the baby's heart is simple harmonic. The motion of the wall of the baby's heart only approximates the simple harmonic. State what is meant by simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out what the frequency is. So the frequency is 142 beats per minute, so it's how many beats there are per second. So you divide it by 60, so it's 2.37 hertz. Omega equals 2 pi f, so it's up 14.9 radians per second. We then can look at our equation sheet and see that the maximum displacement is linked to the idea of the amplitude, and we know that Vmax is equal, therefore, to omega times by a, because sine omega t is equal to 1. So therefore a is going to be equal to the maximum velocity, which you know is 22 times 10 to the minus 3, because we go over millimeters to meters. We divide it by 14.9, which is going to be, when you're working it through there, linking into the idea of the angular velocity. So therefore it's 1.48 times 10 to the minus 3 meters, which is 1.48 millimeters. Again, learn the definition of simple harmonic motion. It is the idea that there's always a resultant force proportional to the displacement of equilibrium position, and the force is always acting towards that equilibrium position. The next question says, a can of spray paint needs to be shaken before being used. The diagram shows a machine designed to shake a can of spray paint. The bracket oscillates vertically with simple harmonic motion. State the conditions necessary for an object to move with simple harmonic motion. When the bracket is oscillating, the distance between the highest and lowest positions of the bracket is 8 centimeters. The bracket completes 270 oscillations per minute. Sketch a graph to show how the velocity of the bracket depends on the time. You should include velocity and time values on your graph. Then determine the maximum acceleration of the bracket, then suggest why the particles of paint in the can will experience a maximum acceleration that's different to the previous answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, like we said before, learn the concept of simple harmonic motion and its criteria. So there's a resultant force that's proportional to the displacement from equilibrium, and that force is always acting towards the equilibrium position. In this next one, we can say F is equal to 270 divided by 60, so it's 4.5 hertz. Omega equals 2 pi f, so it's 28.3 radians per second. And V equals omega r, so it's 1.13 meters per second. And then you can use that to then draw your graph of the values for V and T on the axis, because you've just worked out the maximum velocity that you would require. Next, what's the maximum acceleration? Well, we know a equals minus omega squared a, or minus omega squared r for for working on maximum acceleration. You've got omega from the previous question. You know r, it's going to be 4 times 10 to the minus 2 meters, so it's 32 meters per second squared. Now, why are they experiencing different maximum acceleration? Because the particles themselves are free to move inside the can. So not all the particles will actually move with simple harmonic motion, and because that means the amplitude of the oscillations of the particles will be different to the amplitude of the can. The particles might continue to move upwards as the can starts to move downwards, and then the particles collide with each other, and the force on the pane particles is not equal to the force on the can, so therefore you'll get all different values. The next question says, the figure below shows how the velocity of a 2 kilogram mass was found to vary with time during an investigation of simple harmonic motion of a pendulum. Use the graph below to estimate the following for the mass: its maximum velocity, its maximum kinetic energy, its maximum potential energy, its maximum acceleration, and the maximum restoring force acting upon it. So pause the video now, then unpause the video when you want to go through your answer. Right. So in this one, the maximum velocity is the peak of the graph, which is 0.35 meters per second. The maximum kinetic energy is therefore going to be a half mv squared with the adjusted value of v for the maximum velocity. So you work it through and you get 0.12 joules. The maximum potential energy will equal the maximum kinetic energy because that is the maximum energy of the system. So it's going to be 0.12 joules. So therefore, what's the maximum acceleration? Well, we know maximum acceleration. We know it can work through, okay, from the information given, because we know it's going to be minus omega squared a. We know we can work those through, so therefore we get 0.17 meters per second squared. We know F equals ma, so it's 3.4 newtons. The next question says, show the graph of displacement against time for an oscillator. Okay, sketch the graph to show the variation of potential energy with time and the kinetic energy with time. Then a simple pendulum has a mass of 50 grams. It is initially released from an amplitude of 0.050 centimeters and has a frequency of 0.40 hertz. Calculate kinetic energy 2.8 seconds after release. Then show that the maximum kinetic energy of an object moving in simple harmonic motion is given by the equation maximum kinetic energy is equal to 2m pi squared f squared a. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would it look? So you've got to see that when you have when you've displaced it from equilibrium to start off the oscillation, you'll get a maximum potential. It'll then drop to zero when it's going through equilibrium because it's got no displacement from equilibrium, and it works through like that. Remember again, potential can't be a negative, it's a scalar, so therefore you would never get a graph below the x-axis. Now kinetic energy opposes that one, so it's the opposite one, because when you've got a maximum potential, you've got a minimum kinetic and vice versa. Now next one, you can say omega equals 2 pi f, so therefore it equals 2.5 radians per second. From the equation sheet, x equals a cos omega t, so you pop all those values through to get 0.038 meters. We then can again look on the equation sheet to work out the velocity equation, and you can pop it in to get plus or minus 0.081 meters per second. Therefore the kinetic energy is going to be half mv squared from those previous values, 170 times 10 to the minus 6 joules. Now we know that kinetic energy is equal to half mv squared, so maximum is when they go to Vmax. We know also from simple harmonic motion on the equation sheet, Vmax equals omega a, omega is 2 pi f, so therefore Vmax squared is therefore going to equal to 4 pi squared f squared times by a squared when we sub in the values. Pop that into the equation half mv squared, so therefore we get 2m pi squared f squared a squared. The next question says, a trolley of mass m is fixed to the end of a spring. The spring can be compressed and extended. The spring has a force constant, k. The other end of a spring is attached to a vertical wall. The trolley lies on a smooth horizontal table. The trolley oscillates when it's displaced from its equilibrium position. Firstly, show that the motion of the oscillating trolley is simple harmonic motion, and then show that the period for the trolley is given by the equation t equals 2 pi square root m over k. So, in this one, you've got to prove that a is directly proportional to f, and therefore a is directly proportional to x. So, therefore, We know that the force acts in the opposite direction to the displacement, so therefore it must be simple harmonic motion. Now we know from Newton's second law, A equals minus F over m. It's a minus because we know that the force is always acting towards the equilibrium, so in the opposite direction to the displacement. So now we know in the spring constant, F equals kx, so we can sub that in. And we also know that because it is simple harmonic motion, A equals minus omega squared x, where x is going to be the displacement. So therefore we can cancel everything through. We can say omega squared equals k over m, so omega equals square root k over m. We know that omega equals 2 pi f, so f equals omega over 2 pi. Pop in all the values, work it through, t is 1 over f, so we get 2 pi times by the square root of m over k. The next question says, if the amplitude of a mass oscillating freely at the end of a spring is doubled, what happens to the time period of the oscillation? Then a horizontal spring has one end fixed to a wall and a trolley attached to the other. The trolley is pushed to the right by 4.9 centimeters with a force of 2.8 newtons and then released. It oscillates with a simple harmonic motion with a time period of 0.44 seconds. Calculate the mass of the trolley. Then what would a graph of t squared against k look like for a mass oscillating a spring? So pause the video now, then unpause the video when you want to go through your answer. Right, so you'll notice that the time period of a mass oscillating does not depend on the amplitude of oscillation. So t does not have a value of a in this equation, so therefore the amplitude would not change the time period. Now we know that we're given here the force, okay, and we've got our extension or our change, so therefore we can say k is equal to F over delta L. Remember we turn centimeters into meters, so we get k to be 57.1 newtons per meter. We know that for this case of a mass spring system, t equals 2 pi times by the square root of m over k, so therefore you can rearrange it, make m the subject, pop in all the values, and you get 0.28 kilograms. Now, how would this graph look like? Well, we know t squared is directly proportional to 1 over k because we know that 2 pi and m will be constant in that particular equation. So the graph will be an inversely proportional relationship, and there'll be a line of best fit with a negative gradient becoming less steep, because that's what an inverse proportion graph looks like. The next question says, Skylab was an early space station that orbited the Earth. Skylab contained a body mass measurement device. The device was a chair connected to a stiff spring. Astronauts in orbit around the Earth are sometimes described as weightless, although they do experience a weight force. Explain why astronauts may be described as weightless. Then the spring was tested without oscillating. A force of 175 newtons was applied to the spring, and the spring deformed by 28.9 centimeters. When no one was sitting in the chair oscillated with a period of 0.858 seconds. When one of the astronauts sat in the chair oscillated with a period of 2.26 seconds. Calculate the mass of the astronaut. So pause the video now, then unpause the video when you want to go through your answer. Right, so this one, the idea is the astronauts are moving in a circular orbit, so they'll experience a centripetal force as they orbit. Now, the weight of the astronaut is acting as the centripetal force, is acting towards the centre of the circular orbit. So therefore, the astronauts are free falling, they are accelerating towards the centre of the Earth, okay, as they orbit it, but they'll have inertia in the vertical direction, so therefore they'll be moving in a circle and they'll be free falling, and they'll not be touching any object, they'll not be touching the bottom of the spaceship, so they won't experience a contact force which we would observe as weight on Earth. In the next question, once again, we can work out k by doing k as F over delta L. Remember, we're going to be in meters, so convert our centimeters into meters there, so we get 606 newtons per meter. T equals 2 pi over the square root of m over k, so therefore you can work out the mass by doing the mass when it is not got when it has an astronaut in the chair and an astronaut without the chair. So the mass will be by the astronaut with itself, 11.3 kilograms. Then we've got the mass of the astronaut and the chair, 78.3 kilograms. So the difference between the two is the mass of the astronaut, 67.0 kilograms. The next question says, a simple pendulum has a period of 2 seconds on the Earth. Calculate what the period would be if the pendulum was on Venus, with the mass of Venus being 4.87 times 10 to the 24 kilograms, and the radius of Venus being 6.05 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you can say is we know from the gravitational fields module G equals gm over r squared. So from the information given for Venus, we can work out the acceleration due to gravity on Venus. So it's 8.87 newtons per kilogram. Now we can say that if t equals 2 pi over the square root of L over g, that t is directly proportional to 1 over g square root of 1 over g. So therefore we can actually ratio this and say t Venus over t Earth is equal to the square root of g Earth over g Venus. So you can pop it all through and you do the square root of 9.81 over 8.87, which is 1.05. So it's telling us the time period on Venus will be 1.05 times greater than the time period on Earth. Time period on Earth is 2 seconds, so on Venus it would be 2.10 seconds. The next question says, a simple pendulum can be used to determine a value for g. When the pendulum is displaced through a small angle theta and released, it performs simple harmonic motion about its rest position. The student uses this 85 centimeter pendulum to determine a value for g. He times 3 complete oscillations and obtains a time of 5.61 seconds. Calculate the value of g given in this data, and then express your answer to the appropriate number of significant figures. Suggest and explain one way in which the student could refine the experiment to get a more precise value for g. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we know that the time period is going to be 5.61 divided by 3, because there's 5.61 seconds for 3 oscillations, so it's 1.87 seconds. We know L is going to be 85 centimeters in meters, 0.85 meters. We know T equals the square 2 pi times the square root of L over G. Rearrange, make G the subject, pop in the numbers, and we get 9.6 meters per second squared. Now, how could you get a more accurate value for G? Well, you could time our oscillations because the percentage error in the timing will be reduced by dividing by when you do your number of oscillations. You could repeat it several times and average it out to reduce random errors. You could repeat it for different values of L and plot a graph of t squared against L to find G, because that will counteract random error produced in the experiment. The next question says, a diagram shows a metronome which includes an inverted pendulum used by musicians to set a tempo. The pendulum oscillates with simple harmonic motion and makes a loud click at regular intervals. A faulty metronome stops making a clicking noise. A student tried to check the accuracy of the period of the metronome using a stopwatch. The student timed the pendulum as it moved from one extreme end of the oscillation to the other. Explain how the procedure used by the student to determine t could have been improved. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand that time and a number of complete oscillations and dividing by this time will actually reduce your percentage uncertainty because it increases the time recorded and therefore reduces the effect of the reaction time. You should always time for the midpoint of the oscillation because that's when it's moving the fastest, so it's easiest to identify. You can also use a fiducial marker to identify the midpoint of the oscillation, which is when the pendulum is traveling the fastest, and that will therefore overall make it easier to measure, reducing your percentage uncertainty. The next question says, a data logger is used to monitor the oscillations of a lightly damped oscillator. The results are shown. State why amplitude decreases with time. State one quantity that remains constant for oscillations and determine the natural frequency of an oscillator. The amplitude of a damped oscillator decreases exponentially with time. At t equals 0, the amplitude is 5 centimeters. The amplitude decreases 90% after each period. The period of its oscillation is 1.0 seconds. Sketch your displacement time graph for this damped oscillator up to the time of 5.0 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, amplitude will decrease with time because dampening will dissipate energy out of the system and towards the surroundings, decreasing the amplitude. What stays constant when you have dampening? It's the time period. Now, if you look on the graph, the time period is 1 second, frequency is 1 over time period, so it's 1 over 2.0, which is 0.50 hertz. Now, when you do your displacement time graph, you'll realise that when you think of where the displacement is compared to equilibrium and how it links into the oscillation, it's going to be a cosine graph. You're going to have a time period of 1 second, which will remain constant throughout, and it'll start off with an amplitude of 5 centimeters. After the amplitude decreases to 90% of the previous value for each cycle, so the first cycle is 5 centimeters, the next one is 90% of 5 centimeters, 4.5, 90% of that is 4.1, 90% of that is 3.6, and 90% of that is 3.3, given your particular cycle. The next question says, in some examples of dampening, the amplitude of a damped oscillating system decreases exponentially with respect to time. Determine the initial amplitude, period and angular frequency of the system below, and use the graph to determine if the amplitude decays exponentially. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the initial amplitude is the displacement at the start, which is 0.25 meters. The time period is the time it takes to go from peak to peak, which you'll see is going to be 4 seconds. The angular frequency is 2 pi over t, so it's 2 pi over 4, so it's 1.6 radians per second. Now, to see if it decays exponentially, what you're going to do is take a fixed time period, like 2 seconds, and see if the values at each point is going to be the same. So at 0, it's the displacement is 0.25. At 2, it's 0.21. So you do 0.21 over 0.25 is 0.84. Then do the same from 2 to 4. You get 0.86. Then do the same from 4 to 6. That's going 0.89. The values are therefore similar. So the value of change is constant, which indicates exponential decay. The next question says, seismometers are used to detect and measure the shock waves which travel through the earth due to earthquakes. The figure shows the structure of a simple seismometer. The shock wave will cause the mass to vibrate and cause a trace to be drawn on the paper scroll. The frequency of the typical shock is between 30 and 40 Hz. Explain why the natural frequency of a spring mass system in the seismometer should be very much less than the range of frequencies. The graph shows the acceleration of mass against its displacement when the seismometer is recording an earthquake. What evidence does the graph give that the motion is simple harmonic motion? And use the information from the graph to determine to calculate the frequency of oscillation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when do you get this idea of resonance? So when the driving frequency equals the natural frequency, resonance will occur. That'll give you a massive jump in amplitude, so therefore that'll give a false reading for the shock wave strength because it won't be an accurate reflection of it. The graph below shows simple harmonic motion because it was a straight line through the origin, indicating acceleration was directly proportional to displacement, and because the gradient was a negative, it was in the opposite direction to the displacement. Now, how could you work out the frequency of the oscillation? Well, we know that omega can link in by saying, A is going to be equal to omega squared over r, so therefore omega squared equals A times r. So therefore you pop in the values, you work out omega to be 22.3. F equals omega over 2 pi, so it's going to equal 3.6 Hertz. The next question says, a teacher is teaching her class about the phenomena of resonance. To do this, she uses a drinking glass to produce sound waves in 2 different ways. When the glass is gently struck, the glass emits sound for a short time. When a wet finger is slid around the top of the glass, it is possible to produce a loud continuous sound. Explain these observations. So pause the video now, then unpause the video when you want to go through your answer. Right, so striking the glass will set the glass into a free oscillation. Energy is then transferred from the glass and the amplitude of the oscillation will decrease, and then it becomes damped, so because it's damped because the energy is going to the surroundings. Now if you slide a wet finger around the top of the glass, we've now got a forced oscillation because we've got a driving force driving that oscillation. Now the driving frequency produced by the wet finger is then equal to the natural frequency of the glass. That will then cause resonance, which will allow a maximum transfer of energy into the glass. That will increase the amplitude tremendously and you get the resonance effect. The next question says, an object is suspended from a spring. When displaced, the object executes 180 complete oscillations in a time of 1 minute. The upper end of the spring is then suspended from a mechanical oscillator. The spring mass system is forced to oscillate. The frequency of the mechanical oscillator is gradually increased from 0. Sketch a graph to show the variation of amplitude with the frequency of the mechanical oscillator. Then an old van with an undamped suspension system drives over 3 spade bumps 10 meters apart at a speed of 2.5 meters per second. The front end of the van begins to resonate. State the natural frequency of the suspension and explain why driving over the bumps at different speeds will reduce the amplitude of the oscillations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can work out what the natural frequency is, because it's 180 divided by 60, because it says it's 180 complete oscillations in 1 minute, so therefore it's 3 hertz. So there must be the peak of the graph at that value, because that's when you get your highest amplitude. So as the driver approaches the natural frequency, the amplitude will increase. It reaches the maximum of the natural frequency, that's resonance. Beyond the natural frequency, you'll have your amplitude then drop again, so it'll go back in that curve shape. In this next question, what's the time period between the bumps? Well, they're 10 meters apart, okay? So we can say the time between the bumps is going to be 10 over 2.5, so it's 4 seconds. The time between the bumps is the period of the oscillation, which is 1 over the natural frequency, because it's going to be when it equals the driving frequency. So it's going to be 1 over 4, so it's 0.25 hertz. So that would be the natural frequency, and the driving frequency, which would cause the resonant frequency. Now at different speeds, the time between the bumps will be different, so therefore the driving frequency would change. It wouldn't equal the natural frequency, so you wouldn't get resonance. The amplitude will be lower. The next question says, a body is moving with simple harmonic motion. State 2 conditions that must be satisfied concerning the acceleration of the body. A mass is suspended from a vertical spring and the system is allowed to come to rest. When the mass is now pulled down a distance of 76 millimeters and released, the time taken for 25 oscillations is 23 seconds. Calculate the frequency of oscillations. Calculate the maximum acceleration of mass, and calculate the displacement of the mass from its rest position 0.60 seconds after being released. State the direction of the displacement. So pause the video now, then unpause the video when you want to go through your answer. Right, we've talked about this before. 2 conditions. Acceleration proportional to displacement. Acceleration is in the opposite direction to the displacement or towards the equilibrium position. Frequency is how many oscillations per second, so it's 25 over 23, 1.1 hertz. Acceleration is equal to omega squared a, or 2 pi f squared times by a. Pop in all the values. Remember, 76 millimeters turns into meters, so it's 3.6 meters per second squared. Displacement from the equation sheet is a cos omega t, or 2 pi ft. Pop in all the values. Remember, millimeters turns to meters. Pop in the values, and it's 4.3 times 10 to the minus 2 meters towards the equilibrium position. The next question says, a 150 gram mass was hung from a spring as shown. The spring extended by 7.5 centimeters. The mass was displaced vertically 3.0 centimeters from its equilibrium position and then released. The mass oscillated vertically. Explain why the motion of the mass was simple harmonic motion. Calculate the maximum velocity of the oscillating mass, and explain why the maximum velocity of the oscillating mass decreased over time. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the 2 conditions? The resultant force is always proportional to the displacement of equilibrium, and it always acts towards equilibrium. Now in this next question, think of all the information you've got. You can say F equals mg. So it's 0.150, because we're using grams into kilograms, times by 9.81 is 1.47 newtons. We know the spring constant is F over x, so therefore it's going to be 19.6 newtons per meter. Remember, it gives you centimeters in the question, converted into meters. We know because it's a mass spring system, T equals 2 pi times by the square root m over k. Pop in all the values, you get 0.49 seconds. Omega equals 2 pi over t, so it's going to be 2 pi over that value to be 11.4 radians per second. And then finally, V max is omega a, because sine omega t trends to 1, so therefore it's 11.4 times by 3 times 10 to the minus 2, the amplitude in meters, and then we go 0.343 meters per second. Now the maximum velocity will decrease over time because you've got dampening forces there. They'll dissipate energy to the surroundings from the system, and dampening is when you go work against those resistive forces. The next question says, here is a young girl swinging on a garden swing. You may assume that the swing behaves as a simple pendulum. Ignore the mass of the chain supporting the seat throughout the question and assume the effect of air resistance is negligible. 15 complete swings took 42 seconds. Calculate the distance from the top of the chains to the centre of mass of the girl in the seat. Express your answer to the appropriate number of significant figures. To set her swinging, the girl in the seat would displace from equilibrium and release from rest. Their initial displacement of the girl raised the centre of mass of the girl and seat 250 millimeters above its lowest position. If the mass of the girl was 18 kilograms, what was her kinetic energy as she first passed through this lowest point? And then calculate the maximum speed of this girl during the first oscillation. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, we can say the time period is 42 divided by 15, so it's 2.8 seconds. We know t, because it's a pendulum, is 2 pi over square root L over g. We can rearrange it, make L the subject. We then pop in the values and we get 1.9 meters, and again it's 2 sig figs because you're given two significant figures, 42 and 15, in the question. We know here E equals mgh, and therefore in this case the maximum potential will equal the maximum kinetic, so we'll work through that way. So it's 18 times by 9.81 equals 0.25 equals 44 joules. We know that's the maximum kinetic energy, and equals a half mv squared, so v equals the square root of 2ek over m. We pop in all the values and we get 2.2 meters per second. The next question says, a grandfather clock uses a simple pendulum to keep an accurate track of time. The second hand of the clock moves forward exactly 1 second each time the pendulum moves from A to C, and another second each time it moves from C to A. Determine the length of the pendulum in the grandfather clock that would accurately tell the time. The pendulum is lightly damped. As a result, the clock needs to be wound up once a week. Suggest one possible cause of light dampening in the pendulum. Explain why dampening does not affect the clock's ability to tell time. Then a grandfather clock has a pendulum of length determined in the first part. It is used to tell the time of the Earth's equator, where g equals 9.78 meters per second squared. The clock was set exactly at the right time at 1800 hours on Monday evening. Determine the time displayed by the clock at 1800 hours the following Monday. So pause the video, then unpause the video and you want to go through your answer. Right, in this first one, we do t equals 2 pi times by the square root L over g. We rearrange it. We make L the subject. We pop in all the values. Now again, remember t is 2 because it's going 1 second to one end and 1 second back again, so t is equal to 2. Pop in all the numbers and we get 0.994 meters. Now, because it's lightly damped, what's causing work to be dissipated, work for against the motion, and it's causing energy to be dissipated to the surroundings? Well, it could be friction at the pendulum pivot. It could be internal friction due to tension in the string, or it could be air resistance. It won't affect the ability to tell the time because the time period does not have an amplitude term in this equation, so therefore reducing the amplitude due to dampening would not cause the time period to change. And in this last one, we can say t equals 2 pi times by the square root of L over g. We know L to be 0.994 meters. We know g to be 9.78 because this is the equator. So we work it out to be 2.00306. So that tells us that for each time, when the time period is 2 seconds normally at our position on Earth, it's going to be 2.00306. So therefore we can run it back to 1 second by half in each value. We know in 1 week, the time from 4 p.m. on Monday 1 week to 4 p.m. on Monday the next week is going to be 604800 seconds. So in that time, the other clock is going to move forward a bit less by dividing by 1.00153 because it's going to move that for every 1 second on the other clock. So there's 925 seconds slower than the recording time, which is 15 minutes and 25 seconds. So actually it'll be slower. So therefore over the week you would lose that 15 minutes and 25 seconds. So it would actually say on the clock 17:44 and 35 seconds, which is why you need to always calibrate your clocks. The next question shows, during the final stage of a wash cycle, an undamped washing machine increases the rotational frequency of the rotating drum from 0 to 1250 revolutions per minute. The rotating drum has a diameter of 35 centimeters. Calculate the maximum linear speed that the clothes in the washing machine could reach during the final stage of the washing cycle. Between the rotational frequencies of 600 and 900 RPM, the washing machine can be observed to vibrate. The amplitude reaches a peak at 750 RPM. Explain the shape of the graph shown. Newer models of the washing machine are heavily damped. Describe what you expect the amplitude profile to look like in newer models compared to the graph shown, and then dampening is incorporated into the design of many everyday objects. A set of supermarket scales is damped to reduce the variation in weight measurements when food is put on the scales. State and explain the degree of dampening that's most suitable for the set of supermarket weighing scales. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that you get your Vmax at 1,250 revolutions per minute. Now we know frequency is going to be equal to 1,250 divided by 60, so it's 20.8 Hertz. Omega equals 2 pi f, so it's 2 pi times by 20.8, because that's the frequency, so it's 130 radians per second. The radius is the diameter by 2, so it's 35 centimeters or 0.35 meters, divided by 2, so it's 0.175 meters. Vmax is equal to omega times by r, pop in the numbers, we get 23 meters per second. Now, what's happening? Well, the rotation of the drum forces the washing machine to vibrate at the same frequency. This driving frequency approaches the resonant frequency of the machine, which is the natural frequency of the object, and the machine will resonate and gain more energy from the driving force, causing it to have a violent increase in amplitude of oscillation. Now, what would happen if you have dampening? Well, the first thing is the profile is flatter, so it's got a wider peak. It's not as sharp, so therefore it'll be a duller peak, but also be a lower peak, and also be slightly less as well compared to an undamped model, so the peak will shift to the left slightly. Now, the type of dampening you want here is critical dampening, because what you want is you want your scale to go straight back to equilibrium as soon as possible. That is critical dampening, so therefore it will reduce the variation because the scales will go back to equilibrium as soon as possible, so therefore you need your critical dampening. That brings an end to our revision session today. So hopefully if you found this revision session useful, you can answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics in periodic motion. So thank you so much for attending this revision session on periodic motion. I hope you found it extremely useful, and as always, have a lovely day.